In this video, we will look at how you can represent complex numbers geometrically using vectors, which allows us to investigate properties of complex arithmetic using all the powerful tools of geometry. In fact, it was this correspondence with geometry that ultimately led to the widespread acceptance of complex numbers amongst the mathematical community. Before we look at the vector representation of complex numbers, we better first ensure that we're comfortable with vectors themselves. This will be just a quick crash course, since the Extension 1 course develops the deeper theory. Put simply, a vector is just a mathematical object that has associated with it a length and a direction. Geometrically, we can represent a vector as an arrow. The length of the arrow is associated with the length of the vector, and the direction the arrowhead is pointing is associated with the direction of the vector. We define direction relative to the positive x-axis. Symbolically, we represent a vector using either a bold font lowercase letter or a lowercase letter with a tilde beneath it. We can represent a point in space as a vector by constructing an arrow between the origin and the given point. This is known as a coordinate vector. We can also construct a vector between two generic points in space by connecting the given points by an arrow. The direction the arrowhead points is determined by which point we consider to be the starting point. This is known as a position vector. Position vectors can have an alternate symbolic representation similar to a line segment, but with an arrow above it. Since vectors only have a length and a direction associated with them, we can translate a vector anywhere in space, and its length and direction will be unaffected, hence the vector's unchanged. This is an extremely useful property of vectors, as we're about to see. Consider two generic vectors in space. We wish to determine the vector that results from adding the two given vectors. The resultant vector will be completely defined if we know how long it is and in what direction it's pointing. Well, we can translate the second vector such that its tail aligns perfectly with the head of the first. The addition of the two vectors then just requires us to travel along the first vector and then along the second vector, and the resultant vector is simply the vector that starts at the tail of the first vector and finishes at the head of the second. This diagram is known as a head-to-tail diagram, and it's used extensively in physics. Geometrically though, we can develop a more sophisticated representation of addition and subtraction of vectors. To do this, consider two coordinate vectors as shown. Translate copies of each vector along the other vector, aligning them with the head of the other vector as shown. This produces a parallelogram, since we have produced a quadrilateral with each of the opposite sides parallel. Now consider the diagonal connecting the tails to the heads. There are two possible paths to travel from the tails to the heads, but both are simply the addition of the two vectors. Hence the diagonal represents the addition of the two vectors. And it isn't difficult to see that the other diagonal represents the subtraction of the two vectors, since we travel along one of the vectors backwards. This method's known as the parallelogram rule. Now, since we can represent complex numbers as points in the Argand plane, we can represent complex numbers as vectors in the Argand plane. The parallelogram rule is often used in HSC style questions along with one other powerful geometric result. Multiplying a complex number by I results in a counterclockwise rotation by 90 degrees or pi radians. Combining these results produces squares and rectangles in the complex plane, and thus the properties of diagonals of squares and rectangles become associated with complex numbers. In terms of complex numbers, the modulus represents the length of the associated vector. If we restrict the modulus but allow the argument to vary, then we produce a circle. We can generalize this to a circle with generic center simply by moving the vector to another point on the Argand plane. We can also consider regions in the Argand plane by placing restrictions on the modulus and argument, often resulting in regions with circles and arcs. The geometrical representation of complex numbers as vectors opens all sorts of interesting geometrical properties that may otherwise be hidden. We will see some other astounding geometrical properties of roots of complex polynomials in a future video.